In this chapter, we're going to learn some of the characteristics of acids and bases and take a look at a couple reactions that they undergo. We'll begin by investigating two definitions of an acid. The first definition, the Arrhenius definition, has a limitation. And that limitation is that this definition must be used and must occur in water. Now, looking at this definition, the acid right here forms H3O plus in water. So that's the definition of the acid. And H3O plus is also called the hydronium ion. H3O plus is often abbreviated as H plus. And this can be thought of because if this has to be in water, H plus and H2O joined together make H3O plus. So since this has to be in water, they often just refer to it as the H plus or the proton. Now these acids are most commonly found in two ways when you look at the formula, and a lot of times this is helpful. So the first way is probably more common. You have hydrogen that's in the front of the formula. So examples of this are right next to it, things like HCl or HBr or H3PO4. What these three acids have in common is they have hydrogens here that they can use in an acid interaction with water. The second definition is an organic acid. That also has to have a hydrogen, but it's after a COO. And this COO is attached to some other types of carbons and hydrogens. And then the H will be right here at the end. So for example, acetic acid, which is the acid in vinegar, it's this acid that we're referring to after the COO that will act as an acidic hydrogen and come off in water. So let's take a look at these equations and how the interaction in the water create the definition of the hydronium ion in water. So this first one is hydrochloric acid, and you see the hydrogen here that's in the front of the formula. And the H plus comes off the acid and goes into the water. So H plus and H2O together make H3O plus. And that's what we need to have the definition of an acid. Now if you imagine this H plus is gone, so it leaves the chlorine behind. And so the other product is just the chlorine, which is left behind. Now note that there's a negative sign here. That's because when you remove the positive with the H plus, anytime you remove a positive, you leave a negative behind. So the second acid is nitric acid, and here again is the hydrogen in the front. So this H plus comes off the nitric acid, that's what acids do, and it goes to the water. The H plus and the H2O together form the hydronium ion, which is what makes this fit the acid definition. What's remaining, if you take away the H, and what's remaining is NO3, you see that's the other product. It has a negative because if you take away the positive from the H plus, you have a negative left behind. Now this last example here, this is sulfuric acid, and notice you have two. Sulfuric acid is something we call a diprotic acid because it has two hydrogens. For the sake of this definition, we treat each hydrogen individually. So if one hydrogen comes off, one H plus comes off and goes with the water, again we have the hydronium ion. And what would be left behind, only one hydrogen would be gone, we have HSO4. And there's HSO4 negative because we took away a positive. And every time you take away a positive, you have a negative left behind. You could also have a triprotic acid, like phosphoric acid, because it has three hydrogens that you could get rid of. But remember, for the sake of the definition, we only get rid of one at a time. Now this last example is the acetic acid, and here's the H that comes off. This H plus comes off and goes with the water, just like ours did before, so we get H3O plus. What's left behind, if you take away the H plus, you have CH3COO, which is right here, remembering that it's also going to leave a negative behind when we take away a positive. Now, in one of the homework problems, they ask you a very similar reaction, and they want you to include the state, so I included it here in your notes. But we have the acetic acid, which would then be aqueous. Water would not be considered aqueous. Be sure you include that as a liquid, because aqueous means dissolved in water, so it doesn't make much sense to make water aqueous. When we add the acid to the water, the products are aqueous, so we have the acetate ion and the H-hydronium ion are both aqueous. So this example here, while it's not the specific one that's in your homework, it's like a question in your homework. So it's worth taking a look. So that's the acid. Remember again, in acid, the hydrogen comes off the acid to form H3O plus in water. In this example, remember, in the Arrhenius definition, it has to be in water. Now let's look at the base. So a base has its own definition. And in the base, we don't form the H3O plus, but we form the hydroxide ion. So in the Arrhenius definition, a base forms a hydroxide ion. There's two ways that we can form hydroxide ions. The first one is if you have an ionic compound, it can dissociate. So how I know something's ionic is that if it has a metal, and in this case, we have to have the hydroxide ion with the metal. So here's an example. Right here, that's the first type of metal hydroxide. So sodium hydroxide. Water is put above the arrow because it's not a reactant. You're simply dissolving the sodium hydroxide in the water, and it dissociates into its two ions, the sodium ion and the hydroxide ion. The second type is a reaction with water. We call it ionization. And while there are several bases that react with water, there only is one of them that I would like you to be familiar with. And that's the reaction with NH3, which is ammonia. So when you place ammonia in water, it reacts with the water. And an H+, so think of water as H+ and OH-, the H+ on the water goes to the ammonia. Then that makes the ammonium ion. And if you take H+ away from water, what you have remaining is the hydroxide ion. The presence of the hydroxide ion makes this a base. So now let's complete these two reactions based on what we've learned about the Arrhenius acid and base. They're both in water, and here's the acid, the hydrogen's in the front, so the H+ is going to go to the water. When it goes to the water, it will make H3O+. Now if I remove the H+, what I'm left with is OCl. Because I've taken off a plus, I have to leave a negative behind. Now this is a base. It's a metal, potassium, with the hydroxide ion, which is OH, negative. So we know that we'll dissociate. So really, when I wrote this problem, it would not be written like this. We would have an arrow because it's not really reacting with water. It's just being dissolved in water to fall apart into its ions. While the Arrhenius definition correctly predicts the behavior of many acids and bases, this definition is definitely limited, and sometimes it's even inaccurate. So, we will discuss the second definition in the subsequent video.